My name is Gordon McFadden. I'm an architect at Intel, and we've been doing some work with NGINX and our accelerators. I'm going to present what we did with the acceleration of the TLS, public key exchange. We're doing this demo, or this measurement that we did includes the full payload encryption and full payload compression. And all three of those services were accelerated with Intel. Feel free to ask any questions anytime. I don't have a separate Q&A at the end. Just interrupt. There's some of my colleagues here, in case there's some questions that they know better than I do. We'll try and get you the right answers. We have to study this for about 10 minutes. Okay, I'm just kidding. So I'm going to do it in three ways. I'm going to do a brief introduction to the Quick Assist technology itself. I'm going to go over the bits of the NGINX configuration file that we used for establishing the SSL and the compression, and then the results. So we did this on the Gen 2 technology, which is an accelerator that is PCI Express connected to the socket. It was done with the PCH version of it. It's available as an add-in card. The platform that we used was PCH enabled. It supports lots of different services: bulk crypto, encryption, decryption, verify, compress, decompress. It supports SRIOV, and as I said, it can be as a card or on the PCH. So all of these results that we're talking about, all of these measurements were done with compress and verify enabled, which is a feature that we use to ensure that when a piece of data is compressed, it can be decompressed. So we compress it, and then we immediately decompress it and run a checksum on it to make sure that it's exactly what we expect. It's also with all of the Spectre and Meltdown patches applied. So there's nothing missing from the configuration. This is kind of what our software stack looks like. At the top, we have NGINX. We integrate through OpenSSL. And underneath OpenSSL, we integrate with an engine that's specifically designed for Quick Assist Engine, but it integrates cleanly into OpenSSL. And that uses the Quick Assist user space API. For the compression side, we use QAT zip. And there's an extension to that, which is a shared object. QAT zip is a compression, user space compression library, which uses the underlying Quick Assist libraries to do the compression and decompression and hide all of the details that are required. Quick Assist QAT zip is also designed to work in platforms that don't have acceleration. So you have a common software stack. If some of your servers are accelerated, some are not, you don't have to worry about which software you're installing. It works all the same. Underneath these guys, we have the user space library itself and the USDM, which is a user space DMA-able memory. And that line probably goes to both the QAT engine and QAT zip. We need components of memory that can be DMA to and from the hardware. And so it has to exist. It shouldn't be swapped out while we're in the middle of an operation. And underneath that, we have a couple of drivers. In this particular case, we use the auditory driver. And then we have the hardware. Any questions on our setup? Excellent. So this is how we, for the most part, how we integrated the components into NGINX. So we loaded a module. We actually have a specific module, the QAT zip filter module. And then we just enabled it. in this particular case, it's very similar to the gzip configuration parameters, but there's a few more of them. For example, the minimum size of 128, we don't submit to hardware every single bit of data. If you send 128 bytes of data, it's faster to do that in software than in hardware. Actually, I think that's the same one as the gzip one, the bottom on the software threshold. If we have something under 2K, then we do that in software. We don't do that in hardware, just because it's the overhead of the offload cost is a little bit much. The QAT zip buffers, we're setting up 16K buffers for doing this. The chunk size is what we're sending to the hardware at a time. So NGINX, if you just take it out of the box and you start looking at how the compression works, it sends 16 kilobytes at a time. Then when that compression is done, it pulls 4 kilobytes at a time. So what we do is we pack up at least 64 kilobytes at a time before we send it to the hardware. We send that to hardware, and then we pass it back at 4 kilobytes at a time. But fundamentally, at the hardware level, we're dealing with 64 kilobyte chunks or whatever's left over at the end of the file. So for the SSL, this is a little bit simpler. This is how we load our engine module. We again have a shared object, and we integrate with the SSL engine, and we just put the parameters in there, right? We for the engine, we're saying use the QAT engine. We're going to do it in asynchronous mode. And that's, yeah.
Memory buffers that you're using, is the memory pool that NGINX provides, or is it your own the memory?
Which part of it?
The buffer sizes you were talking about in the previous slide, the zip buffers that you have, is that using the NGINX memory pool that you're managing those buffers, or you manage it in the module by itself?
I think these are managed in the module itself, but I'm not completely certain. But I believe these are managed in the module itself. I think it's intended to be the same size as the buffers that NGINX uses, but by default, I think they are 16K. That's a good question. And the rest of this looks pretty familiar. There's not too much surprise. So we're doing this asynchronously in poll mode, which gives us a pretty good performance advantage. This is the hardware setup that we use for these testing. We use 2 separate platforms. They had 4 10 gigabit Ethernet connections between them. The NGINX platform was sort of like a middle of the road platform. It's a 6138, which has 18 cores, right? 20 cores, okay. And it runs at 2 gigahertz. So it's kind of a middle of the road platform. And it had 16 gigabytes of memory, and we only use 16 of the cores for NGINX tasks. So not a heavyweight machine. And when we were running Apache benchmark, okay, we used Apache benchmark for this, and we assigned 1 Apache benchmark per Ethernet connection. So that's the hardware setup. Very straightforward. Yes. Yes, it's a single socket. It was a single socket platform. So interestingly, if you're running on dual sockets, you can manage the NUMA node through the USDM interface. So you can say, what NUMA node am I connected to, and take memory from that. We support the usage of huge pages in that USDM, and huge pages tend to sort themselves out pretty well itself.
How would the hardware be slot where the hardware goes that with the system? socket. I saw in the original picture you had it on one socket, not the other one.
So the PC, so this particular implementation is on the PCH, and the PCH is connected to socket 0. It is available in plug-in card, so you can connect that to either socket that you want. And in point of fact, it's not uncommon, or maybe it's architecturally possible to put multiple PCHs down on a 4-socket platform and just boot off of one of them, and then have the other I/O components of the PCH available for larger socket platforms. So you can move your if you have multiple sockets, if you have multiple quick assist cards, you can assign them where they make sense.
Otherwise, you would basically be doing compression off of the socket 0, right? Almost always connected to that.
So it's still faster to if you're running. Okay, so that's an excellent question. Okay, and I happen to know a little bit about this. So in this picture right here, right, this is what you're talking about. In this picture right here, yes, if you're going to compress something in the hardware and it's on socket 1, and this is your connectivity, then yes, you're going to go over to socket 0. But that is not a huge cost compared to doing the compression on a core in socket 1. The compression is very expensive.
Yeah, what I was actually looking at was then socket 1 in that case would basically offload all its work to socket 0, and that's the only way you're going to be doing, because every compression that you're going to offload from socket 1 has to come through socket 0.
Yeah. If you're configured this way, then yeah. But that's still.
You're saying that still is better than doing compression on it.
Yeah, we can tell. I mean, you can measurably tell when, at a quick assist level, if you're operating in this manner. You can say, yeah, I'm getting these numbers, and then if I'm mixing up my NUMA, or if I'm intentionally testing off NUMA just so we know what the numbers are, then yeah, you can see that there's a difference. But the cost of doing compression is very high. The same is true with PKE. Cost of doing PKE is very high. And so the benefit of offloading, it still exists there. Good question. And again, like I said, you can, if you've got depending how your PCI lanes are configured, you can set them multiple devices. So, but yeah, like I said, in this case, this is a single Xeon, sort of a mid-range platform. So this is what we were using for the input data. These are all English language news websites, 2 from Asia, 2 from North America. We used different sizes. The ABC News one was, we just picked the first about 5,000 bytes because we wanted to show that you have to show data with smaller data sets and larger data sets. But they're all English language news sites. And the Apache benchmark, for those of you that are familiar with it, that we used is described right here. So we were using AES-128 SHA with TLS 1.2 and compressing. Each of those was running 100 concurrent for a total of 400 concurrent jobs. So what we've said so far, this defines our test setup, our from a software, from an infrastructure, from a hardware perspective, and this is the content that we're using. Any questions so far? Okay, so this is the fun part for me, okay, because this is what our results are. So there's 3 graphs that we're going to show, and they're left to right, a comparison of with software and without software. Software was still with encryption, still with compression, but without the acceleration. So as we can see, you know, the one on the left here is the completion time over the 40 gigabit LAN. With the larger files, the completion time is a fraction of what it was before. So if you have like large data sets, large files, then you know it's quite small, quite a small fraction of it. But even with the small data set, the 5,000 byte one, we're still significantly faster completion time as a ratio of the comparing the blue to the blue. You can see that it's tremendously an improvement over doing software. We intentionally included a file which caused us to jump, where we had to do a CRC combination in software, and that's why you see the jump in the gold one. That was an intentional case where we couldn't seed the CRC engine because of the way we do it. We had to do a combine, and because of the size, and we still get very valid performance numbers here. So one of the metrics that are used a lot here is the connections per second. And we don't have we weren't trying to maximize the connections per second for PKE. This was like a hard end, full-on real use case, and then exactly the same use case using software. And the connections per second in all cases go higher. And with the larger files, you see 4 times the connections per second compared to software. And again, even with a small file, you see a substantial improvement in connections per second with the very small file.
I apologize, but can you remind me from a color coding perspective which is large and which is small?
I'm sorry?
Can you go back to the previous?
Yep. So the smallest.
Yeah, color coding there.
So yeah, that's a good point. I could have color coded these in this slide. So in the following slides, it will be left to right ABC Cable News, Times of India, and Shanghai, okay? So in these guys right here, ABC News, Shanghai, CNN, Times of India. So they go smallest to largest in that order. We've worked with these so long it never occurs to us that people that aren't used to it or haven't dealt with these a long time, it would have been useful to do that in the previous page. But they're in order. Yep. So the third number here is the CPU loading. So with this improved connections per second, with the improved completion time, the CPU usage over that time period is always, in every single case, an improvement. Even with the small files, with the ABC 5K file, you're still clawing back 5% of the CPU usage, and with the largest file, the Times of India, then you're giving up. You're clawing back 34% CPU usage. So, John, do you want to answer that one? Okay, so let me do this. Is John Strang. He's the wizard that did all of this, and the way that his organization works is if we're going to publicly release performance numbers, then they have to be vetted and run by his group. So he's the wizard. Oh, is that what it is?
Yeah.
Oh, okay. So it's 100% of 16 cores?
It's with 16 cores, it's 76%.
But that's 100% of those 16 cores?
Yeah.
Okay. All right. I probably could have known that.
Yeah. He didn't turn off the other 4, so. No, they were both left.
Okay, so you can see even in this case, we're giving back a lot of core availability to do other things with. We use the Quick Assist library in big data as well, and this, represents, an increase in complexity of workloads that they can use, that they can create. So,
I had a question.
Yeah.
So you were doing encryption and compression, right?
Yes.
guys using RSA or to do this?
RSA.
RSA.
Yep. So does that show that? Yeah. So the TLS. Yeah.
Yeah. So OpenSSL uses AES 128 SHA, which implies RSA 2K, which implies RSA 2K with an HNAC SHA. That algorithm. You pass that into OpenSSL.
We can use it ECC as well. Did you guys run any tests with ECC or just all the tests were run with RSA?
So this particular set was run with RSA.
Okay.
Yeah.
What would you predict if this was in ECC?
That's a really tough question to answer. So I think that the software implementations of EC are better than the software implementations of RSA. Have we done any EC measurements?
Yeah, with quick assistant and versus software. So the smaller the file, the more connections you're going to be doing. And if you're doing more connections, then ultimately you start becoming bound by the handshake. If it's quicker on ECC, on software, then say, for example, then you'll see a software. But yeah, the smaller file ultimately, the more PKE operation. So if we're using ECD, RSA2K, this will be higher performing. But the larger the file, the less PKE operation. So it doesn't matter if we're using RSA or ECD.
Thanks, John. Okay, so I think there's the one other test that John did was the core scaling. And the intent here, this is a lower is better. So software versus hardware, right? This is so this is completion time. So lower is better. So the green is quick assist and the blue is software. And what this was intended to show is that there's no funky number of cores or something where we're kind of trying to get the best numbers that we can. I mean, this is straight across the board improvements in performance. And I kind of like this slide because it really shows how much you can get out of a single core, right? I mean, you could do most of your web serving off of 3 or 4 cores. You don't actually have to run that many more. It's kind of cool. For this, we use the concatenated or the first 760K of the concatenated Calgary.
Just untar the Calgary corpus.
Untar the Calgary corpus and
grab book 1.
Okay. Okay, so the last thing that I wanted to show. So this is a slide that I presented last year at NGINX. The only difference here is the fine print has changed. But the graph is exactly the same and the files were exactly the same except for concatenated. And the difference here that I want to point out is that this was strictly compression. This was pre-compress and verify, and this was pre some of the BIOS changes. And the fundamental shape of these graphs are still the same. We see a vast improvement in CPU usage between software and quick assist compression in the same relative order of magnitude. We see the improvement in completion times over QATs of compression times. And this was strictly using compression. This was not doing RSA and not doing bulk crypto. And the reason that I bring this up is just to point out that even adding more services, even doing more things, you still retain the performance improvement picture. We actually went back and redid some of our tests this year to use exactly the same files as last year when we saw the same data coming up. So any questions? Yeah. So this was this the same 10 by 4 last year, John? I'm fortunate enough that John did the measurements last year as well. I think
I'm
it,
not 100% sure what the configuration is in terms of like the I/O for that, but yeah, I don't think I'd have to get out my Excel sheet.
And follow-up question, was the flow director on in terms of traffic?
Like pause frames?
Yeah, yeah.
No, those are
No,
always
not the pause frame, the flow director which binds you to the same code when it sends the connection and the binds information. Intel has that flow director setting in its name, right? I'm just curious whether that was set, did that automatically forwards the packets to the code where originally the packet was received.
So NSI affinity?
No, not the MSI affinity, there's a separate one. The flow director, I'm just curious. That does have a sort of a underlying hidden performance, both sides in the old world. I'm just wondering whether that was originally.
I think we'd have to check. I don't know. Yeah.
Is the compression API for OpenSSL, is that a synchronous API or is it async?
So we're not using the compression API in OpenSSL. We're using a,
Oh, that's separate.
yeah, the QAT zip. And part of the reason for that is NGINX, encrypts and compresses at different points in the processing. The API that we're using for compression is asynchronous internally, but externally it's a synchronous call. So you can pump a lot of data in, and inside of that it's submitting and to and from the hardware asynchronously.
Have you done any tests to characterize the latency of like a software compression operation versus using QAT, in line with some code? I'm just sort of trying to think of another application on NGINX where there's a high compression load, but it's a very latency sensitive. I can't sort of pipeline a bunch of them in parallel.
And you can't pipeline a bunch of them in parallel.
Yeah, like a latency sensitive API, I'm trying to invoke it, I want to shove a file of data over. So I can't use the additional throughput if the latency is too high.
So we do measure latency, right, officially, of the compression API. Do we do that?
AB does provide some type of like.
I mean, just at the QAT API.
Oh, like how many cycles?
Yeah.
Yeah.
Yeah. I think we do that. Yeah.
Yeah.
I don't think we've done a software to hardware comparison, but it would be the hardware compresses really freaking fast. And you can get, if you can't submit a bunch of individual packets from the same application simultaneously, and you're going to be having to essentially serialize them, if that's how I understand your question, you're still going to be in a much better position than if you did it in software. And if you happen to be running multiple applications that do that, then you can achieve the full performance that's available in the hardware itself that way. And in point of fact, that's also similar to what happens in big data applications. They do a lot of processing and a small amount of compression, decompression, but there's so many of them that they do that. They achieve their hardware utilization by having multiple applications running at the same time.
How do you monitor the performance of whether the process is getting a request or whether it's really the CPU that is slowing things down? Is there a way that you guys measure the performance? And what tool are you using to measure that? Because if there is some slowdown on the CPU side, it won't be able to send things faster, right? For whatever reason. I'm just curious as to.
Is there a way to monitor that?
Yeah.
We do have quick assist counters, like firmware counters that we can see when work is being submitted. We can monitor those in real time. Yeah. Okay.
But that's not visible at the Linux OS level.
It is.
It is?
Yeah. Yeah. It's part of the SysFS.
Oh, I see. Oh, okay.
Yeah.
So how much cost commission is available and how much does it cost?
So the question was how much they cost, and I'll introduce Mark Chambers.
They are commercially available from third-party vendors, and a range should be somewhere between 600 to $1,000.
Okay, any other questions? Okay, so I'd like to acknowledge Mark and Joel Schutze and John for the amount of effort that they put in this. This was not a one person's effort, so thanks to them as well. All right, and if there's no other questions, we'll call that a wrap. Last day. Go ahead. Go ahead.
How many compression instances did you define to persist?
So the Lewisburg device has 3 individual PCI Express devices, and each of those has 10 compression engines in it.
And did you assign affinity to each one?
Did you assign affinity?
Yeah, yeah, so we, not to get too deep in but yeah, pretty much.
So the affinity is applicable to interrupt mode, though, right? So you're talking about in the QAT configuration file.
Yeah.
That's
Oh, yeah.
that's applicable at the interrupt level, right? At the callback level.
Yeah, that's not the
Yeah. 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 Oh, at the NGINX level.
Yeah, that's what we did. I mean, we worked with QAT.
Okay.
But in 2017, that's what we did. Setting affinity and using task set.
We
To set affinity at the address level to be able to assign specific cores to specific, like you mentioned before, because we had problems with the network card.
Yeah.
Being different socket than the 13.
Yeah.
So we had to task set assign the same socket to set to both the network card and the 3D card.
Okay, so it's possible I was misinterpreting your question, Amir, but there.
None of the instances of the compression.
Yeah. So there's a core affinity parameter in the QAT configuration file, and that applies to the thread that's doing the interrupt. If you're doing callback, then it's not applicable. And so in all these services are doing callback, right? I know for certain that the QAT zip does, but I think all of them are doing callback. So clearly, keeping track of where your applications are running is important, but I don't think the core affinity comes into play here. Not if you're running callback.
Callbacks are using pole or
Pull. Okay, well, thanks very much, everybody.